this video, we're going to be introduced to the concept of the mole. So as chemists, we often want to know how many atoms or molecules or ions we have in a sample. And there's generally a whole lot, right? This is generally going to be a really big number. And so we'd like an easier way to count or to represent the number of atoms or molecules or whatever it is. And so we want something similar to dozens that are used to count things like eggs. But we need something bigger than a dozen. A dozen isn't nearly big enough to be convenient for us. And so our answer to this problem is what's called the mole. And so the mole is just a really big number, and it works just like dozens do. It's just a convenient way to represent how many atoms or molecules or whatever we have. Now, it used to be that this number, the mole, was defined based on the number of carbon atoms in exactly 12 grams of isotopically pure carbon-12. But not long ago, the mole was redefined as exactly 6.022140076 times 10 to the 23rd, and I say entities because we could have a mole of anything. Now, we don't often have to use all of those significant figures. For our calculations, oftentimes what you'll see us use is 4. So I usually use 6.022 times 10 to the 23rd as the number of things in a mole. But you just have to be careful. If the numbers we're using in our calculation are more precise than 4 significant figures, then we'd want to use more digits in that number. So exactly how big is a mole? Right, 10 to the 23rd, that's a pretty big number. So I have a thought experiment. If you took a mole of periods from one of your textbooks, and let's assume that a period is about 1 millimeter, and I took a mole of those periods and I set them up end to end, how far do you think that would stretch? Would it be less than a mile? Maybe about a mile? The distance from Atlanta to LA? Maybe something big like the circumference of the Earth, or the average distance from the Sun to Jupiter. Or maybe it's longer than all of those. Well, if you were to say longer than all of them, that would have been the correct answer. In fact, if we assume that each period is about 1 millimeter, a mole of periods would stretch roughly 60,000 light years. Right? That's actually greater than the radius of our Milky Way galaxy. Right? So 6.022 times 10 to the 23rd is an astronomically large number. And this is due to the fact that atoms and molecules are incredibly tiny microscopic things. And so in order to have an amount that is sort of macroscopic relevance, we need a whole lot of them. All right, and so we can have a mole of anything, just like we can have a dozen anything. So 12 is to a dozen as 6.022 times 23rd is to a mole. Now this number, 6.022 times 10 to the 23rd, is also sometimes called Avogadro's number. So if I have 1 mole of things, then I have Avogadro's number of things. And so it's easiest to use moles and Avogadro's number as a conversion factor. And so if I have 1 mole of something, then I have 6.022 times 10 to the 23rd of those things. All right, and things can be anything. It can be atoms, molecules, ions, formula units. It can be anything we want. So let's do an example calculation. If I have 4.33 times 10 to the 24th water molecules, how many moles of water do I have? So we would use the mole concept in Avogadro's number as a conversion factor. So if I have 1 mole of water, then I have 6.022 times 10 to the 23rd water molecules. And so we can now do this calculation just like the unit conversions we've done. In this case, we're converting from water molecules into moles. So I would start by writing down how many water molecules I have. And now I want water molecules to cancel out, and I want to be left with moles. So the 6.022 times 10 to the 23rd water molecules has to go on the bottom so that the water molecules will cancel, and then the 1 mole of water will go on top. So the units, the water molecules in this case, cancel out. I'll be left with the units moles of water. And so when I do that calculation, I end up with 7.19 moles of water. Now, there is no device that we have that can measure the number of moles in a particular sample. But a very convenient way of measuring and representing the amount of something is with mass. And so it would be nice if we had a relationship between the moles of a substance and its mass. And for us, it's fortunate that we do. And it's called the molar mass. And so the molar mass of an element or a compound in grams is numerically equal to that element or compound's formula mass. So the units we use for molar mass are grams per mole, and so 1 AMU is essentially 1 gram per mole. As an example, right, if I have the average atomic mass of carbon is 12.01 AMU, if I have 1 mole of carbon atoms, then that will weigh exactly 12.01 grams. Or the formula mass of water is 18.02 AMUs. If I had 1 mole of water molecules, that would weigh 18.02 grams. So we would say the molar mass of carbon is 12.01 grams per mole, and the molar mass of water is 18.02 grams per mole. And so molar mass, again, is most often used, or most conveniently used, as a conversion factor. And so if I have 1 mole of water, that will weigh 18.02 grams. So this will allow me to convert between moles and mass for any substance. Alright, so let's do another example problem. I want to know how many moles of lead 2 hydroxide I have if I have 125 grams of lead 2 hydroxide. And so we need the molar mass, or right, numerically that's the same as the formula mass of lead 2 hydroxide. So the molar mass and lead 2 hydroxide. So the 2 is telling me that the lead is plus 2, hydroxide has a -1 charge, so lead 2 hydroxide is PbOH2. And so that molar mass, the molar mass of lead is 207.2. And then I have 2 oxygens, so 2 times 16.00, and then 2 hydrogens, 2 times 1.01. When I add all that up, my molar mass is 241.2, and then, right, if we were talking about formula mass, my units would be AMU, but I'm talking about molar mass, and so I would use grams per mole as my unit. And I think this is most conveniently thought of as a conversion factor. So if I have 1 mole of lead 2 hydroxide, I have 241.2 grams of lead 2 hydroxide. And now, because we know we're talking about one particular compound here, lead 2 hydroxide, you could leave off the PbOH2 and just say 1 mole is 241.2 grams. But in the types of problems we're going to do later, when we apply the concept of moles to chemical reactions, we're going to be converting from the amount of one compound into the amount of the other. And in that case, it's going to be really important to keep the formulas so we know what we're talking about. And so I'm going to start by getting in the habit here. And so I'm going to say, I'm going to keep the formulas. So 1 mole of PbOH2 weighs 241.2 grams of PbOH2. All right, so I have this conversion factor, and then I was given grams, and I want to know moles, and my conversion factor will allow me to convert between grams and moles. So I'll take my 125 grams of PbOH2, right, and I want the grams of lead 2 hydroxide to go away. So this will go on the bottom, so the grams of PbOH2 will cancel. And then the 1 mole of PbOH2 on top. And so when I do that math, I get 0.518 moles of lead 2 hydroxide. All right, so I've done two simple examples here. I've got another video with more examples. I think I have two videos of more examples of doing the conversions, and we can go from mass to moles to atoms or molecules, or we can go from atoms or molecules to moles to mass. And so check out those other videos for some examples of those types of problems. All right, and then just one final note. Right, so numerically, formula mass and molar mass are the same. Right, the difference is in the units and how we use them. So the units, when we're talking about formula mass, are in AMUs, and we typically use formula mass when we're talking about things on the microscopic scale. So we're talking about individual atoms and molecules. When we're talking about things on the macroscopic scale, in that case, we're generally going to use molar mass instead of formula mass, and in that case, when we're using molar mass, the units are grams per mole. But numerically, formula mass and molar mass are the same.